you for joining us this evening in this presentation about HiLDA. I'm George Yazigi. I'm the Digital Systems Manager at Dartech. I manage the high-performance computing and the software ecosystem for the high-performance computing for the center. I'm going to share with you this evening the few slides, and then we'll try to have some interactive session, hopefully. In case you feel that you wanted to ask an immediate question, please pop it in the chat or go ahead and ask it. And at the end, we'll have a short session for Q&A, if that's all right. So, trying to share my screen. Right. Well, for this, let me disable the video just temporarily. Well, the next gen of high-performance computing. Well, how do we start? And where do we start? Obviously, I'm going to start from the market. And please note that this is by no means a complete material about HPC or quantum computing. However, it only attempts to focus on advantages of using hybrid machines and the challenges facing HPC in general and quantum computing in particular, while I introduce HiLDA. So it's like a comparative presentation. Some of the architectural details are not shared due to copyrights and security. So the HPC market is expecting to grow. It is expected to grow up to 9.44% in the coming few years. And if you compare that growth to the expectations in the global automotive market and the global aviation market, it's almost more than double. So there is I would say, some tendency for companies to adopt HPC computing and to adopt new technologies. And there is an appetite, apparently. So what are the key drivers for the HPC market growth? So we have SPLCs, we have the need for real time, we have to ensure the quality of data. Also, we need to have to crunch numbers, to crunch big data, especially with the explosion of Internet of Things. We have to also, needless to mention, to produce simulations and optimizations. And by the way, simulations during the past 18 months have helped to combat COVID-19 in so many different ways, especially in big data analytics. And we also need to keep some pace with artificial intelligence, machine learning, deep learning, and transform that into probably big graphs. And all of this need to be also within energy requirements and governmental, I would say, new rules for green energy. So governments would expect us to reduce carbon emission, and would also expect us to increase the amount of renewable energy used in HPC. So these are basically the main drivers for the growth of this market. But in my view, there is an immediate need for big data analytics, crunching numbers, real-time applications, and simulations. And all of this in the underlying infrastructure of this, especially when you do simulations, you need to simulate artificial intelligence and big graph and machine learning and etc. So the need for those, I would say, types of drivers and key performance drivers has implied that companies are going to invest more into the HPC market, and hence you have growth. What are the challenges? We have, of course, hardware challenges like Moore's Law. We have silicon supply problem. Everybody probably knows about it. We have also the consumption. As I mentioned earlier, we need to reduce energy consumption and increase the consumption from renewable energy. Also, the deployment of HPC. And one important factor is software maturity. At the moment, HPC has been in the market for quite some time. However, the new wave of HPC, which comes under somehow quantum computing, is basically in its infancy with regards to software maturity. Also, we need to think about competition. Basically, in this whole segment and sector, we have 13 monopolies only, i.e., 13 companies who basically produce HPC products, and basically 4 or 5 companies which are actually focusing on quantum products. And also, one of the biggest challenges is data growth. Between 2017 and 2021, for example, medical data has probably increased 5 times or 6 times. Of course, COVID was a major factor, but nonetheless, this is an explosive increase. And something that is really important with regards to HPC challenges is the skills shortage. We have, especially in the West, we have HPC skills shortages. That means people who are specialized in high-performance computing are becoming less and less available. And some of them are switching their profession, going to another area. And some of them are just not anymore probably interested because they are not keeping the pace. They are not keeping up with the new innovations. And lastly, insolvability. We have to admit that in HPC, we have certain algorithms that do not conclude whatever we do. Although this is not a statement to indicate that we are giving up enhancing algorithms, but there are certain algorithms that do not really conclude, and we have to accept that as a challenge. So 3 types of quantum computing. Why I'm moving into quantum computing? Because I want to compare it to HiLDA, which will come in the next slides. So we have homogeneous machines. These are CPU only. Hybrid machines, these contain GPUs and CPUs. Hybrid quantum, these are a mixture between CPUs, GPUs, and quantum. And quantum machines, these are just quantum machines. And as you can see, complexity increases as we go to the right. So the most complex environment to tackle is quantum only. And basically, if we want to think about quantum computing, we need to always think about it from a hybrid perspective, at least in the 5 to 10 years from now. So quantum computing only is not really practical, so to speak, with the current technology and software. So HPC subtypes, we have Strix HPC, where you have the high-speed networks, you have the high-speed interconnects, you have everything that helps in moving the data back and forth at very high speed. This is like HiLDA. And the other type of high-speed computing or high-performance computing is the high-performance data analysis, in which you just use it for creating data analytics reports without necessarily moving and shifting data across a cluster through interconnects. That means through basically InfiniBand, which is one type of networking that is mainly used in high-performance computing. So the HPC landscape, you can see that artificial intelligence industry is growing. You have around 190 billion pounds expected by 2025. You have a huge increase. I was mentioning the huge increase between 2017 and 2025 is going to be 10 times. And I forecast even more, but this is based on a study done previously. But at the moment, the landscape is that we have cloud HPCs, we have on-premise, and we have public HPCs. Cloud is not really a full HPC. It's rather a service whereby you use Amazon services or you use Azure services. On-premise is like HiLDA, and public centers is like potentially the center that the gentleman from Scotland was mentioning. This is something considered probably a public center. So in general, there are main players, and the top players are at the moment NVIDIA and Intel and IBM. And also, of course, Dassault, but they have a niche market in which where they actually design software for high performance computing. So this is an example of a hybrid quantum computer. So what we have is a mixture between a classical computing element and a quantum computing element. In this case, this is the D-Wave, and D-Wave is designed, actually a Canadian company which designs quantum computing systems, and they design the D-Wave supercomputer or D-Wave quantum computer. They are a very particular case in which they invite you to rewrite your algorithms, you reformulate your problems, and you can create a new, I would say, type of problem decomposition, and then you write new algorithms in order to fit into the quantum computing. But the good thing about D-Wave is that it runs as a backend. So you could be using Azure or HiLDA, and then you could connect to D-Wave and buy a few hours from them to help you co-process certain tasks that can run much faster on a quantum computer, and then return the results to you and keep on using the classical compute environment that you have, and hence the terminology as hybrid. So the hybrid solution, and basically I'm going to mention that into this presentation later, but in general, the hybrid solution is going to stay, and it is going to be basically the mainstream in the coming 10 years, but we'll come to that in a little while later. So here are the main processors, quantum processors. You have the D-Wave, top left. You have the Rigetti, bottom left. You have the IBM Hummingbird, top right, and Google Sycamore, bottom right. these are the main basically hardware, actually the brains of the quantum computer that are being used. And normally, if you want to connect to D-Wave, if you can see my cursor, this processor is going to deal with your quantum computing request. Basically, you send it via a regular public cloud, such as Amazon, or even such as Azure, or even HiLDA, which basically HiLDA is quantum ready, and I will clarify in a little while about that. So what is the anatomy of a quantum computer? And this is based on Rigetti's computing elements. So you have basically a few areas. The computer looks very weird. It looks like the internal assembly of a bulb, but it is not really. So you have the casing, you have the photon carrying cables, and you have the mixing chamber where you exchange helium-3 and helium-4 in order to cool down the system. And you have the skeleton, which is used to circulate the cooling. And you have the brain, or the quantum processing unit, which is a gold-plated silicon chip. And basically, this is what you see here in this is the chip where the white one, this disk, this is the Rigetti's silicon chip where quantum computing takes place. So the main quantum computing models are digital analog. This is very difficult to map data to it, and basically it is used rarely. A universal gate, this is an unstable system because of a lot of noise, and noise has a specific meaning in quantum. So, and this is confined for lab use, and basically this is the Rigetti's style. And the annealing computing is the commercial use, which is basically the D-Wave style, and potentially the one Microsoft is currently building. Maybe it's going to be using the annealing concept. So what are the limitations of quantum computers? It's very difficult to engineer. It is very difficult to program. It's not like in the 60s and 70s when COBOL was difficult, or when Fortran was difficult. But with the current software development kits, they are making it less and less, I would say, difficult. But in general, it is difficult to talk directly to a quantum computer. It is crippled by noise and decoherence, and this is due to the instability in the environment, in the system of the quantum interface. The software is still in its infancy, and the cost is very high. There is less competition. Probably there are only 4 or 5 players worldwide, and skills shortage. And basically, it's not a Turing machine. So it's not based on the principles of a Turing machine. So why do we think that the movement in the coming 5 to 10 years is going to be hybrid machines and hybrid quantum? Because basically they complement each other. So HiLDA is basically a hybrid machine, which is composed of CPUs and GPUs, and it's basically hybrid quantum ready. So if I now plan to connect either on-site or using the public cloud to any quantum backend, I can connect HiLDA to a quantum machine, and therefore I achieve a hybrid quantum environment in HiLDA. but we don't have at the moment that plan because we don't have a use case to utilize quantum computing, and we are at this stage happy to use whatever we have in terms of processing power. Later in the future, if anything arises with regards to having the utilization of hybrid computing, we are ready to do so, basically without any hassle. So what is HiLDA? HiLDA is hypercomputing integrated layer for digital aviation. It is hosted at Dartech, Cranfield University. The name also honors Hilda Hewelt. She was the first licensed pilot woman in the UK, and she had an aircraft facility. She was developing aircraft in Luton, very close to Cranfield. HiLDA is an on-premise hybrid machines, HPC, so therefore it is a CPU plus GPU with possible horizontal and vertical scaling. So we can increase the number of machines, we can increase the specification of each machine, as well as we can scale to either on-premise or in the cloud quantum backends. So HiLDA is, as I mentioned, a strict HPC. That means it has InfiniBand fabric, it has CPUs and GPUs as well. So in general, it uses a very high speed InfiniBand, which is about 200 gigabits per second. So here are the general specs of HiLDA. About 4,500 CPUs, 110,000 CUDA cores, about 7,000 TensorFlow and 15 terabyte of RAM, 2.7 petabyte of storage, distributed using SSDs and high-speed SAS, and also the InfiniBand fabric, which connects all the nodes together using 200 gigabits HDR. And the achieved theoretical flops is 10.2 petaflops using AI combined. And this basically at about 80% it can, or 85%, it can consume about 34 kilowatts. So this is the lineup of HiLDA, what it can deliver in terms of configuration. And let's see how this is reflected in the real life. So to put things into perspective, basically, HiLDA is a 50U machine, although it is not vertically installed, but it's a 50U in the number of U's, so to speak. And basically, you are talking about 14,000 laptops equivalent. So if you take a mid-range laptop, let's say an i7, Intel 7, Core 7, the latest, either generation 10 or generation 11, you would need 14,000. Basically, it's more than 14,000, but roughly I put the number. You would have the equivalent processing power of 14,000 laptops working together if you run HiLDA at around 90% or 95%. So what is the HiLDA software stack? Unlike quantum computers, hybrid machines like HiLDA can basically run virtually any operating system and any application. So HiLDA can run any variant of Linux. It can run any variant of Linux and Unix. It can run any real-time operating system, and it can run Windows. So in general, HiLDA is a multi-purpose operating system hardware. However, in quantum operating system, it is still in its infancy. We have DeltaFlow OS, which is developed here in Cambridge in the UK. And we have the Origin pilot, which is between USA and China. And we have the emulation backends, which are basically developed by Azure Quantum and Amazon Braket. And all these emulations could be basically installed on HiLDA. And I have them already on HiLDA. I have Azure Quantum, the full Q# SDK. I have the Amazon Braket, the full SDK as well. And I can basically instantiate a virtual machine that would send to a quantum backend from HiLDA. So the HiLDA software stack. So we have microservice architecture. This is provided by HiLDA. We provide both architectures, monolithic and microservices. However, quantum computing or quantum computers at this stage do not support or cannot support microservices, and they barely support really monolithic. Their architecture is monolithic. The architecture of the quantum computers is either monolithic or network, but to support monolithic concept of software architecture is still in its infancy, and they cannot support microservices at all. And as you can see, for example, if you have an application which is multipartite and you need to send APIs and send API requests across different listeners, you cannot do it using a quantum machine. You need a hybrid environment or even a traditional environment if you're not interested about speed. So what is basically HiLDA's software stack? At the moment, we use, we heavily integrate Kubernetes and Docker, and we run microservices on top of Kubernetes and Docker. So we are using this architectural design because of the ease of management, because of the ease of implementation, because ease of upgrades, and particularly in terms of when you have security upgrades, you can even hot plug the upgrades without the necessity of bringing down the whole cluster or the machine in question. So we rely heavily on a containerized framework, and that containerized framework actually hosts and runs the microservices, whatever that microservices is. However, we do also support monolithic, and we do have also Kubernetes and Dockers, which are an instance of a monolith environment. For example, as I mentioned in here, we can instantiate immediately a web server like a servlet engine like Tomcat, and with no time, and this will actually reduce the amount of configuration time, the amount we spend into testing also. The microservices architecture and the Kubernetes/Docker is really a game changer in managing applications and in managing software. So also, what is the HiLDA's software stack? We have, as I mentioned, hybrid microservices architecture. However, as also already mentioned, the quantum computers do not support microservices. So what is the hybrid microservices features in HiLDA? We have lightweight containers, and this is what we try to always achieve, to keep the containers at a minimum without delving into complexities. We rather duplicate and replicate containers rather than go into a complexity and the complex configuration of a container. So you would see in many installations more than one container taming together and working together in tandem in order to support one, for example, architecture or one implementation that used to be only supported by one monolithic environment or system in the past. So we try to keep lightweight containers in check, and we try to make sure that we are basically controlling and having a ledger of those containers in order to make sure upgrades and maintenance are done on a decided frequency and scheduled frequency. And we make sure that also security updates are done automatically, and we have a check on each and every update to make sure that the containers are in good shape from a security perspective. We also support multi-programming and multi-languages. That means we support a host of programming languages, from Python to C++ to C# to even Q#, which is used in quantum computing, to all sorts, to even MATLAB, to you name it. And we have the out-of-the-box capabilities. That means the containers are ready once they are pulled, and we do not really need to work on modifying anything. Also, we have the ability to create and push containers that instantiate digital twins. And I was happy to learn that the gentleman from Scotland was mentioning digital twins, because this is exactly why HiLDA uses a software stack like this in order to be able to instantiate digital twins on demand. So we have a security by design. We have the environment is protected by 4 layers of firewalls. Excuse me. Sorry. So the whole environment is protected by 4 layers of firewalls. The most effective firewall, I believe, is the application level firewall, which goes at the level of each Kubernetes, and at the level even at, in some cases, at the level of the microservices, but not necessarily. And then we have also the mediation and routing. Of course, in every microservices, you have to route data in a proper way. Otherwise, your data will become really in an ordeal because of the replication of Dockers or replication of Kubernetes, and you need to make sure that data is prioritized, that, for example, 2 Kubernetes which are supposed to communicate together are given the right priority and the right quality of service for them to be able to do that communication. So we do that using intelligent routing built into the software stack which we use. So hot swapping, so we can hot swap the microservices. We don't need to bring down the cluster. We don't need even to bring down Kubernetes cluster. We can exchange or stop and restart certain services without the need to shut down the whole cluster. And this is very handy because sometimes you need to run certain updates if you are familiar with DevOps and you want to push certain changes, and you don't need to stop the whole system. So all what you need is hot swappability, and you can move the new application or the new change into production as long as you got the sign-off for that without the need to shut down the whole cluster. Monitoring and manageability, this is very important. We monitor for hardware failure, we monitor for software bugs, we monitor for security breaches, we monitor for lots of things. And this occupies a considerable area in managing the HPC. And without the use of microservices, monitoring becomes a hectic task because you will end up with a multitude of logs. You cannot really manage your logs. You need to monitor and manage your logs proactively and detect problems even sometimes in advance without really going into the logs after the problem occurs, rather than to be able to proactively find the issues. And of course, lastly, high availability. High availability is a very important feature in HiLDA. So basically, as long as your cluster is working, HiLDA will basically not fail your data. So you will not be having any data failures because if a cluster, if a node fails, there is always some available nodes which will take over in real time from you, from the failing node. And as a user, you basically do not feel that swap. So you would not really feel the high the downtime. There is no downtime that the user can feel. The system is completely load balanced and high available. So you have nodes that work on load balancing, you have nodes that work on the high availability to have an immediate working backup that contains the correct version of the truth of your data before swapping. And when the swap happens, you basically don't feel the swap took place. So where are we now? Okay, so what do we provide in the HiLDA software stack? So obviously we use DevOps, and our DevOps is standardized on GitLab. We use Python as our major, I would say, development environment. We use also Spark, we use Kafka. Of course, Jupyter is linked to Python. We have C and C++ and even C# we can develop. We have Fortran and Lisp, Perl, and we standardize on CUDA 11.4 for the GPUs. So this is the framework provided by NVIDIA. In terms of simulation, we use MATLAB, AnyLogic, LabVIEW, NetSim, STK Pro, Katia, and Boxar, and even ThingsBoard for IoT. So all of these help us in basically producing all sorts of simulations and all sorts of, I would say, basically create modeling. Because at the end of the day, the main usage of HiLDA is to be able to model the physical space into the digital space. So, and by the way, I do apologize because there are things I cannot show due to copyright and or security. So I'm basically limiting myself to what I'm showing on this slide. So what HiLDA also has embedded into the underlying system is Q#, which is the software SDK from Microsoft. It's basically genuinely or intuitively available through the Python SDK. A Qzit, which is from IBM, Bracket from Amazon, Ocean from D-Wave, PyQuil from Rigetti, and Cirque from Google. All these frameworks are available on HiLDA. So whoever wants to use any quantum backend can do so using HiLDA intuitively without really needing to go into Microsoft Azure or to go into Amazon even. Definitely when you want to pass through the backend system, it depends on your contract with the backend system, the quantum backend system. But in many cases, if you are on a research basis, you can get a free access to the quantum backend system and test your code. So that's in a nutshell with regards to the software available. As you can see, in a hybrid environment such as HiLDA, you have basically the flexibility and the luxury to use those softwares. In a quantum environment, you cannot use MATLAB, for example, although they are trying hard to port MATLAB to some sort of a quantum compiler, but it's not yet ready, to say the least. And then you also don't have the luxury of all those graphical interfaces that you can find in, for example, STK Pro, AnyLogic, and LabVIEW. So this is one decisive factor of why we use HiLDA software stack in a hybrid environment, because we can help the user to produce simulations in a graphical manner. Most of the simulations produced in a quantum environment are later translated into graphics. So during the processing on the quantum system, they do not have any graphics. So they just process and crunch numbers, and then later they translate that and they interpret it, and then they do a presentation for that using some graphical engines. But in terms also of the maturity of the software on in terms of the SDK, all the software development kits in HiLDA are basically mature, and all those that are using Python to support quantum backends are fairly new. So there is a really a good time span that need to pass in order to allow those SDKs to mature and to become mainstream. Here is the GPUs that we use. We use the A100, which are the latest Ampere architecture from NVIDIA. We have several A100s. This contains 54 billion transistors, and it is capable of 2.5 teraops in deep learning. So this basically can translate to potentially 624 teraflops per card at half precision, 16-bit precision. So we also use the HiLDA Intel CPU 6258R, which contains around 8 billion transistors. And this actually produces a huge output for artificial intelligence and machine learning, because it is optimized for that. So if someone is trying to invest in a general purpose CPU, I would recommend using the 6258R. So with regards to HiLDA, this is our cluster. These are 50U clusters, and this is one of the snapshots of how we do the monitoring of all the nodes. And this is the comparison. We took a MATLAB deep learning simulation on a conventional HPC machine. 20,000 epochs times 3 takes about 9 days to conclude, with a consumption of 238 kilowatts. HiLDA hybrid machines, 20,000 epochs times 3 takes about 56 minutes without optimization, and consumption 6.3 kilowatts. If I optimize that, I think we could achieve probably 9 or 8 minutes But just to give you the order of difference when you use HiLDA hybrid machines from using the conventional HPC machines. In a CFD simulation, 149 million cells were basically reduced or concluded in about 7 times less than using Tesla hybrid machines. So the comparison was between a Tesla hybrid machine and the Ampere hybrid machine, the HiLDA GPUs that we use. So we were basically able to reach this kind of reduction in time, almost 7 times faster. So also, what are the limitations? So every system has its own limitations, sometimes by design, sometimes by software, sometimes by hardware. So we have pressure from the regulators to add limitations because they are imposing green energy agendas, and we need to be compliant. That means we need to reduce the consumption kilowatt per hour, and we need to increase the consumption from renewable sources. So this could pose a limitation for older systems, because most of the older systems, i.e. bought before 2020, they cannot really comply because they consume humongous amounts of power. So basically, as of the writing of this presentation, quantum computing limitations are basically due to internal factors, not external factors. It's the architectural design which impose the limitations on such systems and such, I would say, computing machines like quantum computing machines, because sometimes the architecture is not optimized and you need to go back and forth several development cycles in order to optimize the implementation. So also we have an operating system and software stack maturity. In hybrid machines like HiLDA, the operating system is mature. That means you can use, for example, Ubuntu, you can use Debian, you can use any flavor of Linux, preferably Ubuntu, Debian, and Red Hat. However, in a quantum computer, you are stuck with a very limited number of operating systems, and they are really very new. Basically, it's not mainstream to have access, although they are trying to emulate the Linux interface and the Linux command line interpreters, etc. But still, this is a totally new environment, and it is in its infancy. So quantum computing software is in its infancy. At the moment, you cannot access a quantum computer purely. You need to pass by a hybrid quantum machine. So that means you need HiLDA in order for you to be able to produce anything or run anything on a quantum computer. So the other thing is the algorithms. We need to accept the fact that certain algorithms cannot be really resolved with our current technology. And therefore, irrespective of the platform, you may not be able to reach a solution. So this is one also of the limitations. And the last thing I would think about is the industry acceptance. Due to operational costs and building costs and engineering costs, the industry may not accept the quantum computers in the same way other computers were accepted. Remember that we are inheriting a legacy from Microsoft and IBM, when IBM decided to personalize the computer, and of course, Apple played a role and other players played major roles in personalizing the personal computer. And many of the HPC that are available in the market at the moment are basically an evolution from the personal computer into a high performance computer based on commodity hardware. So industry, because of the operational cost and because of the building cost, are still not accepting. Therefore, you have a problem in investment. And also, you have a skills shortage. I have mentioned this so far, probably this is the second time I'm mentioning it. Indeed, there are statistics which really say that if we do not have more people going into this sector in terms of specialty, we may in 10 to 15 years don't find I would say a sufficient number of engineers who are in this domain. And lastly, monopolies. Monopolies are creating a real problem, despite the fact that they are making open source and making the development as open source. And some companies would give money for you to write I would say quantum algorithms and things like that. They help you and they give you funding, but still these same companies are exercising a monopoly. I can mention a few, for example, Google. Google claimed a few years ago that they have cracked one of the hardest algorithms, and they said they cracked it 10,000 times faster than others. And then it turned out that the story was not that accurate. So they were trying to gain more, I would say, market presence and increase their audience based on non-verified information. And then when certain professional bodies such as the IEEE wanted to investigate that, they didn't give them access. So still, we are faced with monopolies, and at the moment we have probably 4 or 5 companies in this arena, in the quantum computing. And why I'm mentioning quantum computing? Because I can see that once as I mentioned, the hardware limitation in a previous slide, we have hardware limitations and Moore's law. And in a previous encounter with the BCS, I had mentioned about Moore's law and how Moore's law is affecting us. At one point in time, very close, we will reach, as you can see here in this slide, we will reach some limitation on how far we can go with the manufacturing process of the silicon die of every computer, of every hardware. And as you can see at the moment, we have reached 2 microns. So we are reaching more, and so when we reach 1, we may not be able, and this is happening early next year, so we may not be able to move really forward in the capacity and in the, I would say, ability of increasing and compounding the number of transistors in a square inch. So this, for example, it uses 54.2 billion transistors on an 800 millimeter square die. So, and this is using probably, I guess it's 2 nan. This is using 14 nanometer. I think this is either 7 or 6 nanometers. The photolithography process. So we will be reaching some limitations by hardware. And the next step, the big next step would be to move into the quantum. However, I still, based on what I have presented and based on research and based on what you read in the computing circles these days, is that the hybrid HPC is here to stay for longer than we can expect. However, there will be a slow migration into the quantum computing. And this is how the road ahead in the coming 5 years. Hybrid machines are here to stay. They will keep on growing, of course, subject to hardware limitations and market forces. As long as the market accepts the hybrid machines, it will remain, I believe. And quantum hybrid will experience an explosive growth, not only considerable, I would say an explosive growth in the coming few years, especially subject to investment, skills shortages, and availability of mature software. And basically, in order for you to make mature software, you need to resolve the skills shortages, because the people who are going to produce that software are those who have the highly trained skills or highly trained people. So with the absence of highly trained people, you cannot produce mature software. And this is why sometimes you will see that the curve that would show you how long it takes to develop quantum computing software, it is going to be elongated along the x-axis because of lack of professional and well-trained people. So I always mention this: the microwave oven did not replace the normal oven. So quantum computers will not replace hybrid machines, HPC. Rather, they complement them. And basically, we need to think about quantum computers as coprocessors for hybrid machines. And this is exactly what HiLDA can do. It can help you to design and develop all your algorithms, all your simulations. On top of that, you could even develop quantum simulations and quantum algorithms and connect them to a back-end system, a quantum back-end system, and run them there. So the quantum computer is acting as a complementary coprocessor for what a HiLDA can produce, and in general for the hybrid HPC machines. So I think that's about it, and I give the floor to Fan, and thank you very much for listening, and I'm happy to answer your questions.
Thank you, George. There are a few questions on the chat, which perhaps if you can help us to clarify. There's one, perhaps more clarification one from Ashok, who want to understand a little bit more, what do you mean by secure by design?
Yeah, absolutely. So when you design an application, you try to implement security measures during the design process and not only rely on firewalls. One example, if you are designing an application that can take two-factor authentication, this is one of the things that could be considered as secure by design, because you will not be relying on firewalls, or you will not be relying on other applications to do that for you. However, you could also have two-factor authentication by using a third-party application. But an application that contains, let's say, two-factor authentication is called secure by design. And this is where Kubernetes and microservices would help you to do just that, because you would be able to either rely on the development and make the application secure by design, or you can rely on integrating a third-party application which would be totally transparent to you as a user into the microservice and inside the Kubernetes. So you do not really feel that the application has been altered or has been changed or has been enhanced. So you would basically end up by applications secured by design. However, secure by design, it means that you integrate elements of security while you are designing the application. And many of the microservices applications are like this these days. Can't hear you, Fan. Fan, you are on mute. Fan, you are on mute. Fan, you are on mute. Can you hear me?
Sorry, yep, I have been too disciplined in muting myself. Yes, Andrew have a comment and kind of try to understand a little bit better around converting a logarithm from traditional to quantum. How hard is it? What does it mean in terms of the way that logarithms have to be structured?
Sorry, what is the question? Sorry.
Okay, so I'll just read directly. So I'm intrigued by converting algorithms from traditional non-quantum to quantum algorithms. Is it hard to do? Is it akin to converting recursive algorithms to flat codes?
No, basically you need to change the to answer your question. This is a very good question, but if I want to answer it, I would need to delve into some quantum computing principles. But talking in general, you need to decompose the algorithm, think about the way the quantum computer treats the bits, and recompose the algorithm based on that. Because in regular computing, we understand that 0 is low and 1 is high in terms of voltage. And this is how we basically interpret everything into a traditional computer. We translate, the compiler will translate your source code into basically zeros and ones. To do that task on a quantum computer, you need to take into consideration the qubit concept, which is the entanglement. So you need to consider the entanglement into how you want to assign which is 0 and which is 1. And sometimes you could end up by having 0 and 1 at the same time. You have two states at the same time, and this is where it is probably hard to achieve. And this is why most, if not all, of the current frameworks, software development frameworks for quantum computing, they are based on traditional computers, which would translate from the normal understanding of zeros and ones into the qubit understanding of zeros and ones. I hope I have answered this without going into the intricacies of quantum computing.
Okay, I think Andrew is happy with it. I think for those folks who have not attended some of the quantum meetings we had before, qubit is rather complicated. I have to confess, I got lost by the time we get to entanglement. So if anybody need help to disentangle, we probably need to refer you to some more quantum experts in another sessions in the future. Right, Peter have a comment that referencing the dependency on IBM Microsoft. He remembered the abandonment of the traditional supercomputers to HPC using commodity hardware in terms of breaking those monopoly. So it's interesting that now you see this as a limitation. Or if Peter, if you want to perhaps unmute and bring the question out directly. Not yet from Peter. Okay. Technologies.
I can give you, if you are hearing me, Peter.
Hello, hello,
Hi.
can you hear me?
Yes,
Yeah,
hi
Peter.
there.
Ah,
got you.
fantastic, fantastic. Hello, everybody. Thank you. George, lovely talk. Very much appreciated. It wasn't so much a question, really, just an observation. I thought it was interesting that you noted in your limitations. You know, you mentioned that you felt the IBM Microsoft history of architecture and hardware was a limitation, and you know, I'm old and crumbly now, and I remember the move away from those traditional supercomputers to this what seemed like a panacea, a commodity hardware. You could build high performance computing environments for pennies with hardware. So I was fascinated by your observation. You felt that was a limitation nowadays.
Yeah.
I wondered why.
Indeed, because at the moment, there is a race of who is going to be to secure the supremacy in quantum computing. And to secure that supremacy, you need to create a competitive environment. And that competitive environment is already there. And this will have, it will feedback, or it will have a negative effect on the progress of quantum computing, because people will have less access to the hardware. Because at the moment, if I design an application for quantum, I do have the software development kit, which is freely available. I have it on HiLDA. I can start my development, but I cannot claim that I have tested it. So if I want to test it, I need to pass by the hardware owners, which is at the moment limited to 4 or 5. So in that perspective, and in the near future, I think with time, they will start even putting more and more limitations to how you can access that hardware. And this will basically backfire on the development and growth. And this would become like a limitation, if that makes sense.
Okay, Peter type in chat that he understand, and thank you for the explanation.
Sure.
Right, just scanning on the chat. If there are any additional questions, comments folks would like to put to George, please feel free to do so.
Or if someone or anyone, if you guys have any particular questions related to high performance computing or even quantum computing, I will do my best to answer it by email if that would be appropriate, because I try to avoid delving into the details of quantum computing, because it can be really boring for the audience. So if you have any questions, please by all means put it through chat, and I will get back to you by email.
Okay, right. I think the questions at the moment have stopped. So I thank you, George, and thank everybody for enjoying the meeting. I think it's a fascinating thing, and it is an ongoing development. From that point of view, within the infrastructure, George created the architecture, created HiLDA, and I'm actually one of the users within DARTech to try to take advantage of that computation. The story is just about beginning, so we hope there'll be more things that we'll be able to develop. And it is in our plan that COVID and everything else allowing that summer 2022, we'll be organizing a visit to the Cranfield University Digital Aviation Environment. And then for those folks who may be able to join us in the visit, probably we'll be able to see and learn more about the action that we'll be able to achieve by that time. So I'll just take this opportunity to thank George again for this really interesting presentation, and hopefully it excites ideas and exchange. And as George offered, for colleagues who may want to keep in touch in the future and connect with George, then please feel free to do so.